Okay, so going to be doing an overview of Unit 7, just everything you kind of need to know that we've learned so far for our test that we're going to be taking tomorrow. So first thing I want to review, since we didn't really do it much in class and it's actually not much in your packet, is going over those interests. So we had two equations for this. There's one that was A equals P e to the RT. And there's one that looks like an A is equal to P times a 1 minus R over N to the NT. Sorry, 1 plus R over N to the NT. So these are our growth ones. So if I'm increasing, I'm going to add that rate here because I'm going up by that amount. Here, my values are positive up top because I'm going to be increasing at this rate. Now, if we're decreasing, or we have a decay function, these are going to change a little bit. A equals P e to the negative RT. So that's how we would know that is a decay for our exponentials here. Now, A equals P times a 1 minus R over N to the NT. Because now I'm decreasing by this amount of rate. That's why we have our minus sign here. So these are decay. I just want to do a quick review of what each variable represents in these. So P, remember, is our principal. That is how much you invest, or your starting value. Now, the next one we see, at least up here, is our R. That's just your rate. And remember, you want it as a decimal. You have to convert it back to a decimal if they give you percent. So if you're at a percent, say they give you 6%, you need to actually plug in 0.06, move that decimal 2 places to the left here. Next thing we see is that N. N is just the number of times compounded. So don't let this part confuse you. It's just saying the number of times that you're adding that interest in. How many times per year? Say it's quarterly, that's going to be 4 times per year. Lastly, T, that's just your time. If you have any more questions on this, you just need to send me a quick email and I should reply fairly quickly unless I'm making dinner or something. Next thing I just want to talk about is the basics of our exponential and our logarithmic functions. I'll do graphing in a little bit. This is just going to be part of our kind of definitions and stuff we know about them. Okay, so if I'm here and I'm looking at exponential functions versus my logarithmic. So these are inverses of each other, meaning these kind of have opposite stuff happening here. So if I look here, first thing I'm going to compare is their domains, ranges, and those asymptotes. So domain, range, asymptote. Now, a domain for an exponential will always be all real numbers. This will never change. So this never changes. No matter if this is transformed, this never changes. The range, on the other hand, is starting out as y is greater than 0. This only changes with a vertical translation. So only if I see something okay, sorry, I had to go grab a charger. So vertical translations, remember, this is the only time our ranges are ever going to change on exponentials. Reason is y equals some base to the x. So that's going to look like if I translate this as something added or subtracted over here. Some value k, positive or negative, changes this. So then it would just be y is greater than that k value. Asymptotes work the same way for exponentials. Y equals 0 though, instead, because it's saying that line that it can't cross, well, if y has to be greater than 0, it can never cross it, it can never equal it. That is this line. The same thing applies as with our range. If it's translated, it's just y equals k instead. Now with our logarithmic, since these are inverses, what that means is I just switch where these apply, basically. So instead of my domain being all real numbers, that switches with my range. So these are going to swap positions here. So my domain now, it's still x values, but it's defined the same way, greater than 0. Now my range is all real numbers. Asymptote, well, instead of being a y, we now just switch it to an x. X equals 0. So now, just like over here, our range and our asymptote are tied to that vertical translation, it kind of does the opposite now. It's tied to our horizontal translation. So say we changed it by some h amount, left or right. Well, now it would be x is greater than h and x equals h. So in our equation, what that would look like would be if I had something log base b of x plus h on the inside here, inside these parentheses, that would be our horizontal translation, and that is the only time these will change. Okay. Now, let's talk a little bit about the graphs of these. So I'm still going to be doing exponential on my left, log on my right, for their graphs. For exponentials, you always want to know whether it's a growth or decay, because that just changes how it looks. So you always want to say, first thing, whenever they give you an exponential function, say, okay, was this growth? So my b was greater than 1, or was this decay? Meaning my b was less than 1 or greater than 0. Growth means if I start on the left, we always read left to right. Well, it's going to start way down here and go up. Every exponential growth function is going to look like this. Decay, oh, well, actually it's going down this time, so I have to start higher up and come down. Now, where it intersects here is always either going to be 1 if there's no transformations, or it's going to be based off of that vertical stretch. So times whatever value you have here. So if I had times a, well, these intersect at that a value. Make sure you're always getting a picture of this in your head anytime you see it. It doesn't need to be accurate, obviously. You just need to get an idea, okay, is this going up, going down? Where is it intersecting? For, if you're graphing these in terms of like a question and it says, hey, graph this, remember, just make your table. I always recommend for growth, -1, 0, 1, and 2. For decay, I always like to do more negatives instead. -2, -1, 0, and 1. And that's just because of that negative exponent rule. If I have something to a negative power, I do 1 over that to the power. So like say -2 here, and I had a function where my a was a 1/2. Well, I'm taking that reciprocal still, so now it's 2 over 1 squared, which would be 4. Now, for our logarithmic graphs, the main thing we need to recognize is that, hey, I'm never going to cross this x-axis. It's coming up like so. And same thing here. It's going to cross typically at 1, but sometimes it depends on what it's being multiplied by, or that a value in the front. That would be up right here. Now, for logarithms, this would be our asymptote, our y-axis here, or x equals 0. For graphing these, I always like to use a pattern that helps me find my points more easily, x and y. If I choose strategic x values, it's going to make my y values very easy to find. So remember, logarithms equal the exponent. So what if I have a log base b here, and I say, well, I'm going to do b to the -1, b to the 0, b to the 1, and b squared as my x values. Well, my y values would just be equal to these exponents, so -1, 0, 1, and 2. Now, this may seem a little confusing, but remember that negative exponents just says do your reciprocal. So say I had a log base 3 of x, my x and y's here, I'm just doing the reciprocal of 3, so a 1/3. Here, b to the 0, that's actually always going to be 1, because anything to the 0 power is a 1. B to the first power, 3, b squared, 9. Now my y value is just -1, 0, 1, and 2. I could have picked any number as our example, and this would have worked out. So once again, questions here, go ahead and just send me a quick email. Okay, so next we are going to be looking at solving equations. So if you take these, the whole point of learning about logarithms is actually so that we can solve exponential equations. When I have an exponent with a variable in it, I have to use logarithms to solve it. So what we're going to do here for solving, we have my way, or as Oscar likes to call it, the Dunnigan way, or Oregon way, or whatever you prefer. Okay. Etc. And then we'll have the textbook way. So we're going to go and look at this my way first for solving exponentials. So solving exponentials here, that's equations where I have like b to the x equals y. So y is some function with x in it. I have an x in my variable. I want to solve these. So what I'm going to do is, let's say I'm solving something like a 4, and I have an x plus 1 up here, and that's all equal to 5. So what we're going to do is just use our conversions that we learned when we first learned about logarithms. If I have a logarithm with the base x equals y, well, my base of my exponent is the same. Logs are equal to the exponent here equals x. But now I'm going this way instead. So here the base is 4, so that's going to be my base of my logarithm as well. Log base 4 of that opposite side, this y over here, which is 5 in this case, equals x plus 1. Last thing, I'm solving for x, so I just need to subtract the 1 to both sides. Be careful when you're doing this though, that 1 can't go inside the logarithm. This is a unit, I can't do anything with it. It's here, it's stuck, it's trapped, they stay together. So it's just going to look like a log base 4 of 5 minus 1 equals x. Now we're done, we found x. One note, be really careful with your notation. I see a lot of people trying to write, okay, they'll do the log, they get their 4 really good, but then they're writing 5 like it's an exponent way up here. Don't do that. It's just of 5, it's a regular number, it's going right next to it, log base 4 of 5. Another common thing that I'm seeing in terms of the notation is we'll also just write log 4 of 5. This needs to be down as a subscript. Okay. Now, if I'm solving logarithms, so instead of starting as an exponential, we're starting as a logarithmic function. That's going to be like, I have a log base b of y equals x, like I had up above, and I want to solve for something that is over here. So, let's say I have a function like a log base 4 of a 2x minus 1 is equal to 2. So what we're going to do first is we need to convert it just like we did up here, but now we're starting at a log, we're writing it as this exponential. So the base of my log is a 4, so I'm going to just write that here. First step, write your base. Now add on that exponent, 2, equals 2x minus 1. From here, I'm solving for x, so first thing I need to say is, okay, that 4 squared is going to be a 16. From here, it's just algebra. Add 1 to both sides. 17 equals a 2x, and divide by 2. Cancels, x equals 17 halves. And you can leave it here. Now, we could potentially do this in some real-life situations. We had one example in the homework, which I know a lot of people struggled with, so I want to talk about that down below here. So it was one that was all about elephant prints, and it was saying, hey, solve this equation for A instead of L, or vice versa. So here it is. I'm just going to do it on this paper here. So we have this equation that they give us. L is equal to 45 minus 25.7 e to the negative 0.09a. So solving this one, it's saying, hey, your variable's up here, and we want to get it out of that exponent, and we want to solve for this in terms of L instead. So first thing we need to do is get our base by itself. I need to isolate this e to the negative 0.09a. So following our PEMDAS, I have to deal with subtraction first. L minus 45 is equal to a negative 25.7 e to the negative 0.09a. Now, our equation has a lot of negatives in it. Be careful. So looking at this, I don't know where any of my highlighters went. Here we go. I have a minus sign here, negative up here. Be really careful. You have a lot of negatives. Don't drop them. Next up, I have multiplication here, because remember, our goal is to isolate this for this part first. So divide by that 25.7, but also negative here. Negative 25.7 cancels. Now I have an L minus 45 divided by a negative 25.7 is equal to an e to the negative 0.09a. Here is where those logarithms come into play. So if I'm looking at this, I have an exponential function, variable is in my exponent. I need to go through and say, okay, I'm going to rewrite this as a log. To rewrite this as a log, okay, my base is e. So remember, a log base e is just ln. So I'm going to take this, I'm going to have an ln here, that's my new base of something, and it has to be equal to my exponent, so I'm going to put that over here. So whatever is left goes on the inside, L minus 45 over negative 25.7. We're almost there, we've almost found A. Last thing is to just divide. Negative 0.09, negative 0.09. That right here is our final equation. So we can rewrite it if we want here. Natural log L minus 45 over negative 25.7 all over negative 0.09. Now, this is really nice to have because now it's saying, hey, we're giving you lengths, you can tell us the age. So another way they could have done this would have been, hey, we're not going to make you rewrite this first. We're just going to say we're giving you 36 as your length. Plug it in, solve for your age. It'd be the same exact steps here. You would just have an actual value inside your logarithm at the end instead. Okay. We have two more things we're going to go over. Recursive rules and data classification. So we'll do the recursive rules first. These ones, really, please just don't overthink them. Recursive rules are saying, hey, you have some form of exponential equation, a times b raised to the x. This is our exponential form. You can write this as a recursive rule. I'm just going to do RR for recursive rule. It has two parts to it. my initial value here, and then my rule. Whatever our rate is times our previous value. So that's why you always need to know where you started, because you're going to say, hey, here's where I started. If I multiply that by my rate, it can tell me what my next one is. Sorry, this should have been an n here. So the way these relate is this right here is your initial value. So that's why it's here as well. Now your rate, this is actually just your b value. So this is your common ratio. So if I said, hey, we know that y is equal to a 3 times 2 to the x, my recursive rule would be f of 0 is equal to 3, and f of n would be equal to a 2 times f of n minus 1. So what that's saying is if I wanted to know f of 1 here, I would do 2 times f of 1 minus 1, which is a 2 times f of 0, which, oh, I know that's a 3, so this is actually 6 here. Now, say I started with a recursive rule instead. Say I knew, okay, your starting value is 10, and f of n is equal to a 5 times f of n minus 1. Well, this 5, that's my common ratio. This 10, that's my starting value, a, b. So my equation is going to look like ay is equal to my a value, 10, times my b value, 5, raised to the x. Another notation thing I've noticed with exponentials that seems to keep continuing is we keep trying to write it so it doesn't look like an exponent. We're writing things like 3 times 2x. That just looks like multiplication. These are not the same thing. Make sure you're putting that x way up in your exponent here so we can tell and aren't going to get it confused with multiplication. Now, data classifications, remember there's a couple of rules for this. We have a few different equations it could be. Could be linear, could be quadratic. We've also learned exponential. Now linear, you have a constant first difference. So that's saying if I take each of my y values and I subtract them, they'll have some number in between that stays either the same, or if it's a model for real life data, it's approximately the same. So it's like 2, 3, 2, 3, 3, 2, 3, something like that. Whereas quadratic, it's going to have a constant second difference. Lastly, exponential. This one actually has a constant common ratio. But if it's real life data, that can sometimes be really hard to see. So we actually look like, what I like to look at is that difference in the first. Is it increasing? Increasing? If the yes, then okay. Oh, sorry. Increasing, then check your second difference. So if your difference of the second one is also increasing, approximately, remember, real life data won't always follow this exactly, but if it's approximately increasing here as well, exponential. So what that's going to look like in real life data, so for linear, it's going to look like, oh, I have x values, y values, these are just going up by 1. But say I have like 0, 2, 4, 6, 8. We can pretty easily see this pattern. I went up by 2. That difference was plus 2, plus 2, plus 2, plus 2. Our first difference was constant. It was constantly 2. Whereas for quadratic, our data might look something like, sorry, let me get this set up. Say we started at 0. Well, went from 0 up until 1, so that was a difference of 1 here. But now say it went up to 3. Oh, well, that was a difference of 2. Okay, well, now it went up to, sorry, I'm thinking of this in my head. Went up to 6. So that was a difference of 3. Goes up to 10. Difference of 4. Goes up to 15, difference of 5. But now, if I look at my second difference, oh, well, it went up 1, it went up 1, it went up 1, it went up 1. My second difference was constant, so this is going to be our quadratic. Exponential now, if it's beautiful, perfect data, 1, 2, 3, 4, 5, 6. We'll say we start at 1, then we're at 4, then we're at 16, then we're at 64, on and on and on. Those get big. I don't want to do them quickly in my head. Well, here, times 4, times 4, times 4. So if you can see a pattern here where you see multiplication, oh, it's multiplying by 4 each time here, this is going to be that exponential. But this isn't always going to be super nice. So say this was some real life data. We're looking at like years for our x value, y values, our sales or something. Say, okay, well your sales are in hundreds, so say this was 1, and then the next year, okay, say we sold 2, we doubled our sales, yay. Well, the next year it was 3.5. Well, the next year it was a 7.5. And then the next year it was 16. And then the next year it was 32. Well, if I look at the differences here, plus 1, okay, got a plus 1.5. Here, we're going up 4. We're going up about 9 and 8.5. And then here, we're going up 16. Well, this increase is increasing. If I look down below and find that second difference, 0.5, okay, 3, sorry, not 3, 2.5. Here, 4.5. Here, 7.5. That is also still increasing. This is going to be that exponential model again. So that is the last thing I'm going to be doing for this video. If you have questions or get stuck going through that review sheet, remember that's due tomorrow, just email me. I'm going to have my phone on me all night, I promise. I should respond, hopefully, fairly quickly, depending on what I'm doing.